Okay, so today we're talking still about chemical evidence of these materials. This idea of combustion, arson, explosives, and nuclear weapons will also have physical evidence. But in this portion, we're focusing on the chemistry. So for drugs, we talked about the chemical, the drugs themselves. We talked about their effect on the body. Today we're talking about combustion, the chemistry of combustion, what makes a fuel, how it might be used or become evidence in terms of arson. And then explosives. What kind of explosive molecules are there? What are their features? Should you, come across a molecule, would you look at it and say, wow, that's either a drug or an explosive? There's certain functional groups that you would look at, kind of like we did with the dyes and the pigments. We had the triaromethynes and so on, and the nitro groups. And then because of my background of working for the government for 4 years before I got this job, looking at counterterrorism and even the most dangerous weapons would be nuclear weapons. What kind of evidence would you have chemically of something related to not just a bomb, but something that might be nuclear, either a dirty bomb or a full-up nuclear weapon? So just looking at the chemistry of all of these things, going from a small piece of gun cotton all the way up to a thermonuclear weapon. So quite a range of topics today. And so this is the overview. Combustion is the second most common forensic analysis behind drug and tox. So the most common evidence that you'll get as a forensic scientist will be something related to drugs or toxicology. But then the second would be things collected from fires. There's quite a few fires. I always want to pull some evidence to send it to the lab just to see if it was an accelerated fire. And so we'll discuss that today. Then we'll go through combustion basics, get you refreshed on your ability to cancel units. And so you're used to stoichiometry from Chem 1. Okay, we revisit that today in an amazing way. I mean, it's you don't know the skills you have until you put them to the test. Then we discuss fires and explosive detonations. Lots of videos today, and so I may cut the video up so that I don't get copyright struck, because I'm going to post this as a forensic video, but then it's going to contain other videos from other creators. And so this is the thing that's needed to have sustained combustion. So fire is a chemical reaction that's sustaining itself. And so how do you get a fire started? Like in this room, we have oxygen. We have quite a bit of oxygen in this room. We have combustible materials. We have a plastic cart. We have wood countertops. We have fabric. All of those things are flammable, and they are in an oxidative atmosphere. So we have all the makings for a fire, but we don't have the activation energy. So you have to get it started. You have to overcome this activation energy. So you typically have to put in heat to get it started. And then once it starts, it's exothermic. So the heat coming from the reaction gets the remaining materials over the activation energy. And so it's self-sustaining. Once you get it over the top of that hill, then when it drops down, the exothermic nature creates more combustible material. So you have the fire triangle: fuel, heat, and oxidant. We have fuel and oxidant in this room, but luckily we don't have the heat needed. If we had a heat source, then we might catch on fire. The fourth thing that's needed, I think, that belongs in the fire triangle, which would make it not a triangle, but that is mixing. So if you can separate the fuel from the heat or the oxidant from the fuel, then you can stop the fire, and that's what's going on with our firefighting techniques. So we can spray water, mist, on the fire, and that steals the heat because you've got water droplets that take the heat to evaporate the water. So that steals the heat and cools things down. CO2 powders, because CO2 is heavier than air, it can displace the oxygen. So if you spray CO2, it'll cover it in a blanket of carbon dioxide, and it'll push the oxygen away. And powders, it's a powder that comes blasting out of the fire extinguisher that decomposes with heat. So sodium bicarbonate, if you spray that on a fire, that bicarbonate will break down and produce CO2. It was kind of funny. One time I was at work and I got a phone call. My daughter was like 1.5 or so, and she's sitting in the little children's seat at the table and Jennifer's feeding her and the daughter's looking over there and she's like making faces, like little kids do, but it was an alarm face, and Jennifer turns around and some flour had been on the stove and it caught fire. So it's just a little bitty flower, like a little bit. So she comes blasting at it with the fire extinguisher. Of course, the stuff, that powder went all over the kitchen. And so then I get this phone call. Is the stuff in a fire extinguisher bad for you? A random question. So, why do you ask? She's like, well, there was a little fire on the stove. I probably shouldn't have used it, but I blasted it. And so this yellow powder was everywhere. And so we cleaned it up. And I still don't, to this day, know if it's toxic or not. Probably not. They wouldn't sell it to you, right? Toxin is the dose, right? So, yeah. So we cleaned it all up, yeah. Foam, also a kind of thing. It'd be suspended, these suspended powders in foam. So they'll use that for jet fuel fires. Again, it takes away the heat, but also destroys the mixing. It separates the oxygen from the fuel. And then halogens. So halogenated compounds. Why do we have to segregate our waste in organic chemistry? It's because the carbon-chlorine bonds, carbon-bromine, carbon-fluorine, take so much energy out of the fire that they'll put it out. So if they're trying to use this waste toluene and waste benzene and everything and blend that into diesel, they don't want dichloromethane in there. They don't want chlorobenzene in there because it's going to reduce the fuel ability, the burnability of that fuel. And it's also going to create HCl inside the engine, and it's corrosive. And so they don't want halogens mixed into that waste stream because halogens reduce the heat given off by burning and eventually can even put it out. So here was a thing called a fire grenade. I saw this on the wall at Texas Tech. They had an old, in their pharmacy school, like an old pharmacy from the 1800s. And on the wall it said, fire grenade. And I was like, what is a fire grenade? So I went over there and read the little thing, and this was a little grenade full of carbon tetrachloride. So CCl4 in this glass grenade, and it said, throw at base of fire. And so that's an old school fire extinguisher. It's a glass bulb of carbon tetrachloride. Yeah, now it's going to generate hydrochloric acid, so don't stick around. Okay, but throw it and run. But I thought that was a pretty interesting fire extinguisher. Let's just throw carbon tetrachloride at it. Probably not what you want to do, but nowadays, go for the red canister with the handle. Don't just take a 4-liter bottle of carbon tet. Dr. Williams told me this will work. And so let's look at this combustion continuum, because we have different kinds of things that are related to combustion. We have fire that just burns gradually, and you're familiar with fire. Think of a candle, okay, or a propane stove. And then we have gunshots. So we have gunpowder inside a cartridge that propels a bullet, and that's the key. It's propelling a bullet, so it's a propellant. It's not an explosive, okay? And then we have explosives. We have like plastic explosives, C4, different kinds of explosive formulations that detonate. And so there's this range of behaviors. There's burning, there's propelling, or what we call deflagration, and then there's detonation. So those are 3 different regimes. And so this burning, flame, deflagration is just extremely fast burning. And then detonation is a shock wave that goes faster than the speed of sound. And so this is the row here. This is from the previous book that we had. We have fire, we have explosives, and then we have firearms and propellants in the middle. And so the speed of the burn is subsonic for burning and supersonic for explosives. Now, speed of sound is the speed of the sound in the material. So the speed of sound depends upon whether it's a solid, liquid, gas. It depends on the different materials. And for a powder, it depends on how tightly it's packed, and so on. So we're dealing with the shock wave being faster or slower than the speed of sound in that material. So think about what sound is. It's material crashing into material. So if I'm speaking, my vocal cords are vibrating the air, and the air is bouncing off of other air. There's little waves of pressure that are going through the air and hitting your eardrum and making it vibrate. Okay, so the speed of sound is these pressure waves, and they bounce into each other based on the speed of the molecules. So if I have helium in here, the speed of sound is faster in helium because the atoms are lighter and they're moving faster on average. And so also there's less resistance in helium, so your vocal cords can vibrate faster in helium because it's a lighter atom. And so that's why your voice goes up in helium, because your vocal cords can vibrate faster and produce a higher frequency pattern, and then it comes out into air and then goes in. So that's why you sound funny, like Mickey Mouse or something. You have helium in your lungs. Then if that shock wave moves over towards supersonic, this is really hard to imagine. At least it's hard for me to imagine. You've got a powder. You have the beginning of a burn. It transitions to a detonation, and the shock wave runs through the material faster than the molecules can actually hit each other. That's weird, isn't it? How does the shock wave go through the material before the molecules have time to move? Right? Because speed of sound is the molecules, molecule A hits molecule B, that hits molecule C, that hits molecule D. So that sound wave is going from molecule to molecule collisions. But a detonation, the shock wave goes through the material before the speed of sound, faster than the speed of sound. And so it's really an energy wave. I don't really like the word shock wave, because shock wave sounds like it's moving and bouncing into something. So an energy wave moves through the material faster than the speed of sound, and it's energetic enough to break all the covalent bonds. So think about a molecule. All of a sudden, you don't have any bonds. No atom is bonded to any other atom. So you've taken all of these covalent bonds, you've broken all of them, so you're now at this really high energy state of just atoms nearby each other, and they're going to form their most stable compounds. Most of the time, those are gases. So if you have nitrogen in a molecule and it's next to another nitrogen, it's going to form dinitrogen with a triple bond. Very stable molecule. And now you've got gaseous nitrogen in a solid molecule. And the density of a gas is about 1,000 times less than the density of a solid or a liquid. So that material wants to take up 1,000 times more volume. And then it's hot, so it wants to even take up more volume. So that's what happens then with the expansion wave of the material. The energy wave, or the shock wave they call it, goes through the material faster than the speed of sound for a detonation, and then you have the expansion of the hot products, and that causes the explosion and pushes things. So let's look at some of the different videos. I don't need to play a candle burning. You can imagine that. But this is gun cotton. The burning, so that cotton, the heat from the burning created this pyrolysis zone. And we saw that in the cotton. It turned black. So pyrolysis, what is lysis? Breaking. Pyro, heat. So it's breaking up that molecule with heat. And the cotton itself is the fuel. So the heat from the burning creates this pyrolysis zone, and it's the decomposition of the pyrolysis zone that makes the fuel. So it's the gaseous molecules coming off of this decomposed cotton that are mixing with oxygen and generating an exothermic reaction that sustains burning. Now we have also, this is in PChem 2, these are the results of our QSPR lab. And I just show this because it's a pretty nice equation. If you just want to know how many kilojoules per mole come from a substance, we took the CRC handbook, it has 900 compounds in it, roughly, and we fitted the combustion enthalpy to the molecular formula. So we just did a linear regression. How many carbons, how many hydrogens, how many nitrogens, oxygens, and came up with this equation up here. So the delta H of combustion is equal to this equation, which is just based upon the molecular formula. So we start out with just in general, fuel giving 32 kilojoules per mole, and then 426.9 kilojoules per mole of carbon, and 88 kilojoules per mole of hydrogen. We have this weird number here, 1 per mole of nitrogen, and that's because some of the nitrogens were NH2s and other nitrogens were NO2s. The NO2s actually give you energy, but the NH2s take it. So that's why nitrogen kind of cancels itself out and gives us this low number. And then oxygen, if we have oxygen already in the molecule, it actually takes away heat from the delta H of combustion. And this is delta H of combustion with reacting with external oxygen. Okay, so oxygen balance is helpful for detonation, but putting oxygen in the molecule and then reacting it with oxygen, you've already kind of partially reacted the oxygen. So when everybody's really excited about ethanol and fuel, be aware that ethanol and fuel, adding the oxygen already to the molecule, you get less energy from it. You get less heat. So you lose 163 kilojoules per mole of oxygen that you've put into the molecules. And this is pretty good regression. This is our model based on the just based on the molecular formula, and here's the literature values. So this is a pretty good fit. And so this just tells you, if you know the molecular formula, you can calculate the delta H of combustion. I give you this equation just for you to use on your homework and on the exam, just because it's a nice, quick way. No matter what molecule you're given, if you know the molecular formula, you can calculate how much heat is given off per mole. If you're given the mass of the molecule, you could calculate the molar mass. Okay. And so this bottom one is a QSPR, the molar mass. What is this one? Well, 12.01 times the moles of carbon. That tells you how many grams of carbon you have, grams of hydrogen, grams of nitrogen, grams of oxygen. And so this is the specific heat in kilojoules per gram for a substance. Again, based upon A, B, C, and D, the molecular formula. And so you see most of the organic molecules are around 42. What are these down here? These are molecules like ethanol and ethers and esters and acids. They're already partially reacted with oxygen. You see how much less heat they have if they've been given oxygen already in the molecule. And then these, this is like methyl radical, C2, CH2, and hydrogen, H2. So this is kilojoules per gram, and because hydrogen is so light, you get 120 kilojoules per gram. And so you can see why people say, wow, we want to run our economy on hydrogen because you get so much energy per gram. But the thing is, you don't buy hydrogen by the gram, you buy it by the volume. You know, and so it's very non-compressible. So it's not a great fuel. In order to get the same amount, like 400 miles of travel time in a vehicle, you'd need a tank that had about 9,000 psi of hydrogen if you wanted your car to be about the same size. So I don't want to drive around with a tank that's at 9,000 pounds per square inch of hydrogen. That's not cool. So there's some problems with that. Even though it looks energetically favorable, there's some physical and engineering problems that we have to overcome to use hydrogen. So right now we're pretty well stuck with hydrocarbons, and those are 42 kilojoules per gram. Pretty good energy density. So these are tools of the trade in talking about the heat given off. You take that enthalpy of combustion and you multiply by the mass divided by the molecular weight, so the mass of fuel. And so the fire marshal will come through. He knows this delta H of combustion is roughly 42 kilojoules per mole, or I'd say 42 kilojoules per gram. And he can look around in the room and add up, in his estimation, how much mass of burnable material we have in the room. And this room really doesn't have that much burnable material. It's got this desk, you know, shoot, it may, you know, weigh a couple of 100 kilograms, okay? You've got these desks, they have plastic tops, okay? And so you might add up a few pounds of those desktops, but there's really not much else in the room. But he walks into my room and my office, what does he see? Books, and carpet. Yeah. My desk is metal. Well, actually, I got a new desk, so now it's wood. So I have, and so sometimes the fire marshal comes in and he says, he hasn't here, but in my last job at Pentex, he came in and he says, you got to get rid of some of these files. Because there I had files everywhere. He said, because you've got in this room 1, 2, 3, 4 sprinkler heads. And the fire marshal knows how much heat that's missed can take away. And he looks at the room and sees how much heat this much mass with that enthalpy of combustion can give. And if the combustible load in the room is higher than what the sprinklers can suppress, then you're out of balance. And so he would look at my office and say, you've got one sprinkler head and it can kill so many joules of energy, and yet you've got way more paper in here than that sprinkler head can go. So what does that tell them? If there's a fire in my office, it's going to spread. It can't be contained to that room. And that's what they're kind of concerned about. They can say, all right, this room, if there's a fire in here, it can be contained by these 4 sprinkler heads, and we won't lose the whole building. We'll just have this one room. They have time to get here and add extra water to shut it down, and it won't have spread to the next room. Yes?
And when it comes to the schools, I know that they don't have like sprinkler heads inside their rooms, but they're not allowed to have so many feet above, like, to the ceiling, and is that because of just the dissipation of heat?
I don't know about the thing to the ceiling. But I do know there's if they don't have a sprinkler system, and it's a certain size building, so I think if you go over 15,000 square feet, you have to have a sprinkler system. So a lot of them will build 14,000 square foot places just because it's so much more expensive to add a sprinkler system. They'll have interior walls that are thicker and built out of fire retardant material so that will burn out. It'll burn through an outside wall before it burns through an interior wall. And then they'll have partitions in the attic. So if it burns through the ceiling, is this ceiling connected to that ceiling? We had an older apartment complex over by, it's on 19th Street, over by the Mormon Church. I don't know if there's some apartments over there. They were an older construction, and then it's a 2-story apartment building, and there was one attic over the whole place, and the whole thing burned to the ground. So one student had a fire in one apartment, and it burned everybody's place to the ground because it had a common attic. Of course, now they don't construct them that way because, again, you want that to be contained in one spot. If one student has a grease fire and they throw water on it and it sets their whole place on fire, you don't want that to burn everybody's place down. You want just that place to be contained. And you want it to burn slow enough so that the fire department can get there and get it calmed down and put out. Yes?
I think about like I think it's about like 1 to 2 feet. You can't have anything within 1 to 2 feet of the ceiling like that.
Okay. Okay.
I think it's just because that actually is a flammable material that's close to the ceiling and then can reach the ceiling.
Yeah. Yeah, and so the heat, if it's burning here, the heat will dissipate on its way up. And up there, it's right next to the ceiling. Yeah. It's yes.
Makes me severely question my high school homecoming week when we covered all the hallway walls in complete paper.
Yeah, that's right. Yeah, we get away with a lot of stuff, but the risks, if you're a fire marshal, you're walking along and everything you see, you're like, oh my gosh, this place is so dangerous. I never really thought about it until I worked at a place where the fire marshal came around once or twice, a year. And so then these are the tools of the trade. Ideal gas law for the expansion of the gases. The amount of force that's put on it, so the number of moles times the temperature of the production, so the max burning temperature. And then this one here, the stoichiometric ratio, this uses the amount of balance of the fuel and oxygen in the system versus the perfect or stoichiometric equivalence. And so you should be able to calculate these things. So let's do a few examples. So what is the stoichiometric equivalent for methane in air? Now, we're getting away from chemistry and into fire science. And chemists love moles. We're the only ones. Okay? Everybody else likes mass. Okay? Things they can measure, what I call lab units. And so we need to take, instead of moles of methane, we need to deal with grams of methane. Instead of moles of oxygen in air, we need to use grams of air. And so here's our combustion reaction. Methane and oxygen make CO2 and water. And so our mole stoichiometric ratio is 1 mole of methane per 2 moles of O2. But we don't have O2, we have air. Okay, and we don't want to talk about moles, we want to talk about mass. And so the mass ratio is what? So let's calculate that. How many moles of air will provide 2 moles of oxygen? So you need to know this. This is basic science. You need to know what the atmospheric composition is. Okay, at least to three significant figures. Mainly the oxygen's 20.9 or 21% in air. Okay, and this is in dry air, so water's not included. And then nitrogen is 78%, and the balance is argon with a little bit of CO2 thrown in. Okay, so it's about 1% argon, 21% oxygen, and 78% nitrogen. Okay. And so if we need, 2 moles of oxygen, how much air do we need? Well, you've just got to use these ratios here as a conversion factor. So you have 2 moles of oxygen needed, and this is the amount of moles of oxygen in moles of air. So 9.57 moles of air will give you 2 moles of oxygen. So you should be really comfortable at converting using units. Just find the units and how they cancel. So just go back to your freshman chemistry. You know you have moles of oxygen. You know you need moles of air. And so moles of air has to be on top so that moles of oxygen is on bottom. And just use your units to guide your calculations. So what is the mass of this air? How much does 9.57 moles of air weigh? Well, then we've got to take into account all of these main components. So we have 0.781 times the molar mass of nitrogen. 0.209 is the ratio of oxygen times the molar mass of oxygen, and 0.09 is argon. And so this is the mass of 1 mole of air. Okay, so that's the molar mass of air. 28.9 grams per mole is our grams per mole of air. And so multiplying that by 9.57 gives us 277 grams of air. So that's going to be down here for our stoichiometric amount. That's going to be the amount of air that we have. And then we need our mass of fuel. So 1 mole of methane, what's the molar mass of methane? Carbon's 12. 4 hydrogens, so 12, 13, 14, 15, 16. So that's close enough. 16 grams of methane is our fuel. The mass of our oxidant is 277 grams. So that's 0.057. 0.0578 grams of methane per gram of air, or 5.8% by mass. This means by mass. And so that's a good number to know. 5 to 6% of a fuel mixed in air, and you are at the stoichiometric amount. That's the most dangerous situation you can be in. And we would call that an explosive atmosphere. Now, unfortunately, they're using the word explosive, but this is, again, from a fire science side of things. It just means you get an atmosphere that could go up and, blow the building. It looks like an explosion, but it's really not a detonation. It's just enough to blow the windows out and blow the roof off. Okay. So we call that an explosive atmosphere when you have about 6% of fuel in air. Now we calculated this with methane, but remember with the delta H of methane per gram and ethane per gram and propane and all the way up to buckyball was still around 42 kilojoules per gram. So they all give about the same heat per gram. So if I could disperse to 5 or 6% of just straight carbon in air, it's going to give about the same. So this is a good number to know. 6% of fuel mixed in with air is an explosive atmosphere. 1 spark would make it go. So here's a use of that. Would a 5 liter per minute gas leak reach an explosive concentration overnight? So 8 hours. So this would be the kind of calculation you could do using these values. So 8 hours of this gas leak at 5 liters per minute is how much mass of natural gas, which is methane. So use your units. What do you have? You have 8 hours, and what do you want? Grams of methane. Okay, so just start working it out. Start using your units. You know that 1 hour is 60 minutes. Okay, and we've got this leak in 5 liters per minute, and so that tells us the volume of methane. So we're out of time, and now we're into liters. And then we need to know what the molar volume of methane is. 24.4. We're dealing with room temperature and 1 atmosphere. So you could use the ideal gas law to figure out what the volume of 1 mole is. And so 1 mole is 24.4 liters using the ideal gas law. And so that tells us how many moles have developed. 16 grams of methane per mole. I realize this looks easy because I'm doing all the thinking for you. But you should be able to work your way through the units and just say, where am I and where do I want to go? And you just do it one step at a time. How do you eat an elephant? 1 bite at a time. So work your way through. So now we have grams, and then we're going to, have kilograms, right? So we have 1.57 kilograms of methane that have developed in this house, over 8 hours overnight, 5 liters per minute. And so how much air is in that house? Well, here we need to make some assumptions. And so if you were doing this problem, you would have to tell me what your assumptions are. And so what's the normal height of a room, just a regular room?
8 feet.
8 feet's a good one to use. Okay, my sister's house has like 16 feet ceilings, but it's a nice house. But most just generic, you grab a house out of the suburbs, it's an 8-foot ceiling. So 8 foot, what's the square footage of a regular old house? Yeah, maybe 2,000 foot square house, 2,000 square feet. And that's a good size house. So many are smaller, but there's a lot larger. So let's just go with a 2,000 square foot house with 8 foot ceilings. So that's a volume, right? That's cubic feet. So we're dealing with now the sort of the airspace. We should subtract the walls, but this is a good estimate. So you would write this out, assuming a 2,000 square foot house, assuming 8 foot ceilings. What if you said 10 foot ceilings? You just tell me what you're doing. Assuming 10 foot ceilings. 3,000 square foot house, right? It's not specified in the problem. Okay. So how many liters in a square foot? Well, you might have to figure this one out. There should be a conversion factor from standard to metric that you have memorized, okay? So you may want to write this one down. What's the definition of an inch? An inch is actually defined in the metric system. It's 2.54 centimeters. By definition. So that does not limit your significant figures. That's a definition. So we've defined now an inch is 2.54 centimeters. And so you could figure that out and get it over to liters with some work. Then we have the molar volume of air, and then we have that molar mass of air. So now we've gotten out of moles of air into mass of air and convert to kilograms. And so we have 536 kilograms of air. So we want to look at this ratio and see if it's 6%. Remember, 5.8% was the explosive ratio. And so we have this kilograms of fuel over kilograms of oxidant. Okay, it's 0.00293. And so the stoichiometric ratio was 0.05, and this is much less than that. So this would be too lean. Now, it would stink badly because natural gas has that odor molecule in there. A little bit of methane sulfide, it's thiomethane, so CH3SH. And so it's a nasty smelling substance. And so this would be enough to drive you out of the house you know. Now the downside is you don't wake up with smells. That's been shown many, many times. You think you would. A lot of people will die in their sleep because of smoke inhalation, and you would think I would have woken up. Maybe not. But if you did wake up, that smell would drive you out of the house before it got to an explosive atmosphere. Okay. And so you should be able to do these kinds of calculations. So the downside of this, though, is that we calculated the whole volume of the room, but methane's lighter than air. And so it may rise and become an explosive atmosphere up near the ceiling. Or ether or some kind of paint stripper or something like that is heavier than air. So dispersed into all 2,000 square feet times 8-foot ceilings, it might be too lean, meaning it has too much oxygen and not enough fuel. But if it travels over to an ignition source, then it could flash back, and it could blow up. So this could travel along the ceiling, hit a light fixture, you turn on the light, a tiny little spark, and boom. Okay, so crawl out of the house. Don't turn on any lights. You smell gas. It has to be really strong, though. You're not in danger. Just open the windows. But then also heavy sources would flow down or stay near the bottom. So this stoichiometric ratio is the basis for the LEL and UEL. So that's the lower explosive limit and the upper explosive limit. And this is listed on a lot of material safety data sheets. We used to call them MSDSs, now there's just safety data sheet. And it'll have the LEL and UEL percentages for these substances. And so when you're right at that stoichiometric ratio, you have this phi of 1, you're at the maximum explosive conditions. If it's too high, you have too much fuel. We call that rich. And if it's too low, we call that lean. And so you're safe at 0.25. So 0.25 of fuel to oxidant mixture. Safe at this phi value, 0.25. If phi is 1, then you're super explosive danger. Rich generates lots of smoke because you have incomplete combustion. Lean, you don't have the ability to sustain the flame. Yes?
So some of them, so you're, with the air is 29 grams per mole, so it's sinking, and then the methane rises, right?
Mm-hmm.
So let's just say average Joe does not have a chemistry degree and doesn't know, but if he's in his house doing something and he needs to crawl out because there's a fire about to happen, how does he know whether to sink low to the ground or stay upright?
Yeah, it's a good question. Probably just going to run out, but if it's overwhelming and you're getting dizzy, and you may have to try either. If it gets worse when you squat down, you're like, okay, it's heavier. I just need to get out of here. Yeah, mostly you're just going to fly. Fight or flight. It's going to take over. You're going to fly. Get out of there. But firefighters would need to know if this is a heavier substance or a lighter substance. They would determine whether they, how they attack the fire or the conditions. Let's talk about oxygen balance now. This is a strange calculation. Okay, you have this sort of classic combustion reaction, but notice this one doesn't have oxygen on the left. This molecule is decomposing to produce CO2, water, nitrogen, and oxygen, and this oxygen number could be negative. If it's negative, then you need oxygen on the left, right? But if it's positive, you have all the oxygen you need plus more. And so let's figure out what this oxygen number would be. And so for nitroglycerin, here's the formula for nitroglycerin. You have 3 carbons, 5 hydrogens, nitrogen and oxygen. So 3 nitrogens and 9 oxygens. So this is nitro groups stuck on there. We'll see a picture of the molecule later. And so we put it in this equation. We generate the 3 carbons make 3 CO2s. The 5 hydrogens make 5 halves water. Okay. And then there's some nitrogen. So you have 3 halves of the nitrogens. And then the oxygen, okay, how much is it? So we have 9 moles of oxygen on the left. Somebody follow that. That's easy. We have 6 moles of oxygen here for the CO2. And we have 5/2 oxygen here, so 2.5 moles of oxygen here. And then how much O2 is needed to balance this out? So I have 6, 7, 8.5. 8.5 moles of oxygen, okay? And that's not equal to 9. So I get 8.5, I add another 1/2 a mole of O, which is 1/4 mole of O2. Okay. So this has a positive number here. So we have 0.25 moles of O2 excess in nitroglycerin. And that is really, why it is just so sensitive and so complete in its combustion. So you hit it with that hammer, it's complete detonation. There's no carbon left, no nitrogen and so on. It's all CO2, water, nitrogen, and a little bit of O2 coming off. So there's actually O2 coming out of that reaction, a little bit. Now TNT is also an explosive. It also detonates. But if you'll notice here, here's TNT, 7 carbons, 5 hydrogens, 3 nitrogens, and 6 oxygens. So up here, nitroglycerin has 9 because it's nitro groups, and these are nitrate groups, and these are nitro groups. So doing the oxygen balance, we have 6, and then we have 14 oxygens from the CO2, 2.5 oxygens from the water, and then you add those up, so we have 14, 15, 16.5 moles of O. And how do we get that to equal 6? Well, we have 10.5 too many on the right, okay? And so we need to take away 10.5 oxygens to get it to balance 6. Now, 10.5 moles of O is 5.25 moles of O2. And so we see we have a deficit. This is a negative number to get this to balance with the 6. And because it's a negative number, that means we're deficient in oxygen. That doesn't mean it won't detonate, but it does mean it won't detonate as vigorously as it could. Okay, so this TNT